Swayam Prabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering Module 1 Review of Basic Thermodynamics. So, in the first lecture we have given the fundamental concepts of thermodynamics, systems, surrounding, first law, steady flow devices and so on. Now, in this lecture and continuing our discussion further, we will also move on to some other fundamental topics like which are going to be used for our subsequent modules. So, in this lecture we will touch upon the topics, that is second law of thermodynamics, and it also talk about Carnot cycle, that gives the concept of heat engine. Then second law of thermodynamics also introduces another thermodynamic property, that is entropy, and this entropy has a definite relationship with respect to irreversible nature of a system. So, to quantify the irreversibility, then you will define the topics, that is entropy, and what will again happen if the process is reversible, what will happen to this entropy. So, this concept will be discussed here, and again coming back to the application sides, we will touch upon some fundamental aspects of pure substance, that is properties of pure substance. This is mainly required because in our subsequent module we will be talking about steam power systems, where we will be frequently using water as a working fluid for and in a steam power systems, and it continuously changes its phase from liquid to superheated regions. So, to address those concepts, we will briefly discuss some introduction topics of pure substances. Then in the last segment, we will also talk about some other aspects of second law, that is exergy, which is nothing but the work potential of any form of energy. And to quantify exergy, we also need to define an efficiency called as second law efficiency. So, these are the gross outline of this lecture. Now, let us move on to our main the first topics, that is second law of thermodynamics. So, prior to this we have introduced the first law, which is nothing but the conservation of energy, and with thermodynamic viewpoint we say that energy is available either in the form of work or heat. But then issue is that which has higher quality. So, that is not clear in the first law, but first law of thermodynamics rightly do the all kinds of energy auditings, like energy can be converted to in any other forms, but it does not talk about which is of higher quality and which is of lower quality. So, for that it introduces the concepts of energy transfer either in work mode or heat mode. But again it was found that when energy conversion takes place from work to heat, it is found that we can have a complete conversion of energy from work form to heat, but reverse was not supposed to be true, because that means heat can be considered as a low grade energy, and so what work can be considered as a high grade energy. But this kind of statement does not appear in the first law of thermodynamics. So, for that we introduce the topic second law, that means when the heat is to be converted to work and complete work conversion is not possible, then where is the rest amount of work that is going. So, and some cases it is a unavailable energy, and some cases if at all has to be work, it has to be converted, how much what is the upper limit of these conversions. So, all kinds of answers that we are going to get in the second law. So, there are two concepts here in the second law. First thing is that we are going to introduce a Carnot cycle, which gives the concept of heat engines. That means, modality of harnessing or extracting work potential from heat or work from the heat source. And second aspect that we are going to talk about is a thermodynamic property entropy to quantify the unaccounted energy where it goes. So, and this also is defined through a term what we call as irreversibility. And another additional topic that we are going to concern about this is that exergy. So, in the first law we talked about work energy is available in various forms. So, mainly kinetic energy, it can be a potential energy, it can be a chemical energy, it can be heat energy. So, but work potential of each form of energy is different. Work potential means what is its maximum potential of amount that work that can be extracted from these forms of energy. So, that is termed through a term called exergy. Now, when you define this exergy, we have to bring the system and surrounding into together, then only we can say that what is the work potential. So, these are the some of the topics that we are going to touch upon in this lecture. Now, coming back to the second law of thermodynamics, it is unanimously accepted by two fundamental statements, that is, one is Kelvin-Planck statement, other is the Clausius statement, and they are available, the statements are available as they appear in most of the almost same in all the books, fundamental books. So, I will read those statements, and in fact, these are the negative statements of second law. And of course, violation of there are two statements basically, one is Kelvin-Planck statement, other is Clausius statements, and both are negative form, but violation of one statement also violates the other. So, when you say Kelvin-Planck statement, it talks about a cycle which operates in an engine called as heat engine. So, it says that it is impossible to construct a device which will operate in a cycle and produce no effect other than raising a weight and exchange heat with a single reservoir. That means, while when we propose a heat engines and it takes energy as input from this heat source, and without rejecting it to any kind of rejecting it from this heat engine, work cannot be extracted. So, here there are some terms, when you say operate in a cycle means it has to operate in a continuous manner. So, it is not like instantaneous, it is a continuously operating. And when you say rising of weight, which means it is doing work, because by definition we say work is viewed that in some form we can raise this weight. Then we can think of exchange of heat in a single reservoir, which means that only heat is added, there is no heat rejections. So, this is possible only in the first law with 100% thermal efficiency, but this is not true with respect to second law. The second statement that talks about that when it is impossible to construct a device that operate in a cycle and produces no effect other than the transfer of heat from cooler to hotter body. That means, without giving any work input to a device, we cannot transfer heat from a low temperatures reservoir. So, this is the this concept is mainly meant for refrigerator. So, both this particular figure shows that violation of one statement will also lead to the violation of other. The next topic that is going to introduce for the heat engine is the Carnot cycle, because that is the Carnot cycle which was essentially proposed for second law, and it only tells that the modality or method or mechanism in which work can be extracted from a heat source. So, this particular figure shows that we have a high temperature reservoir source which is available at temperature Th, and we have a low temperature reservoir which is available at TL, and our main objective is to produce is to take this heat from the high temperature reservoir and produce work. So, for that we need to devise a we need to have a cyclic device, that is called as heat engines. So, this heat engine operates with an working fluid that continuously takes heat from the high temperature source reservoir, and it also continuously rejects it to the sink. So, through this process we can do this energy auditing or first law analysis, which will give you the net work output. So, this is exactly what we do in all kinds of power plants, IC engines, all these devices. So, this cyclic manner of operation, which means that in order to extract work from a heat source, we must operate a cyclic device. So, this is the general statement for a heat engines, but when you put with respect to the efficiency viewpoint, because the Carnot cycle also says that what will be the maximum efficiency for these heat engines. So, to do that, what analysis it was proposed, that a hypothetical cycle, the Carnot cycle, it was proposed that if you want to operate that cyclic device, how it should work. So, that cyclic device should operate in 4 processes, which are shown in this pressure, volume and temperature entropy diagrams. So, the first one is reversible adiabatic compressions. So, when you say compression process, that means we are giving work in. So, that is a work input in this compression. So, this is a adiabatic process from 1 to 2. Correspondingly, since it is a reversible adiabatic, so entropy remains constant. So, it is a vertical line shown in the temperature entropy diagram. Then second one is reversible isothermal heat addition process. So, isothermal heat addition, that is process 2 to 3, where heat is getting added, which is say QA, and third one is, that is 2 3 is QA, heat addition. Third one is reversible adiabatic expansion. So, its expansion means it is a power producing device, that means W out. So, essentially this W net that was proposed in the Carnot cycle is nothing but W out minus W in. So, this is the net work, that means cyclic device that is going to produce, and last one is the reversible adiabatic heat rejections. So, cycle will be completed only the state of the system goes from 4 to 1. So, to complete the cycle, some heat must be rejected, that is QR. Now, without this heat rejection, so this is nothing but this heat comes from the high temperature source, that is TH, and heat is getting rejected to the low temperature sink, which is maintained at TL, and through this process we are getting W net work output. So, this is how the cyclic device should operate, and for that reasons we can subsequently we can say that heat additions can be expressed by multiplying this entropy change, that is S3 minus S2 into TH. Heat rejected also can be found out. So, ultimately it leads to the fact that what will be the net work output and what is the thermal efficiency of these heat engines. And with respect to Carnot cycle, we have this ratio, that is QA by TH is equal to Q rejected by TL. So, this ratio holds good, and based on that we can have this cyclic efficiency that can be defined. So, this talks about a concept that if an engine has to operate between a high temperature source TH and TL, this will be the maximum possible efficiency. Now, one more important point here that to be noted is that if you say hot temperature source is TH and that T2, that is that cyclic device operates, that means here TH is equal to T2 and that is equal to also T3, and here also TL is equal to T1 and that is equal to T4. This is the assumption that Carnot cycle makes, and that assumption is only true when the processes are reversible in nature. Then moving further, we are now going to define another term which is entropy, and that comes by virtue of the fact that complete conversion of heat to work is not possible. Then where does this heat goes? So, we introduce some situations where we cannot have complete conversions. So, you need to define some kind of irreversible nature of the process, and that is called a degree of irreversibility, and that can be either external to the cyclic device or internal within the internal components of the cyclic device. So, this irreversibility can be classified as external or internal. Now, the external irreversibility occurs for mainly regions by heat transfer, because whenever there is a temperature difference, then only heat transfer is possible, will be possible, and due to this heat transfer heat reversibility is introduced, and the friction in the machines, this is also a kind of irreversible nature. Another kind of things is that mixing process, throttling process, because cyclic device requires some kind of valves, regulators. So, there for which we need to have a thermodynamic parameters that needs to be specified. So, that is going to change. So, with respect to thermodynamic viewpoint, main sources of irreversibilities are friction, heat transfer, throttling and mixings. So, this is a particular case where we say diesel cycle, and since it is a cyclic device, we are going to say that we can in which we can put the location of the state points that normally defines a thermodynamic processes, and a working fluid can be part of the cycles which continuously takes heat and also rejects heat. Side by side it produces work output, and such, and this particular cycle is a diesel cycle, which is a fundamental air standard cycle for a diesel engine. Then moving further, to quantify the requirement or nature of irreversibility or degree of irreversibility, we are now going to define the term entropy, which is very common, which we have been using frequently, but the main significance of this term entropy is that this is something like analogous to a non-flow reversible work, because when you say reversible work with respect to first law, this delta W, that is work transfer, can be considered as a PDV form work. That means, when you say rising mass, so that is we can put the integral form, that is pressure times change in the volume when you integrate it, and that you term it as a non-flow reversible work, but that was introduced in the first law. Now, when you define the term heat, because heat is the main culprit or main parameter that is going to be addressed in the second law. Now, if through how in the similar fashion or similar analogous manner, how do you define the reversible heat? So, for that reasons we introduce a diagram called as temperature entropy diagrams, that will also tells about the same thing like a delta Q, which is the integral of TdS. So, which other way means that area under PB diagram represents non-flow reversible work, and area under the TS diagrams represents non-flow reversible heat. So, and for an isentropic process, obviously it is a reversible adiabatic. So, delta Q is 0. So, TdS becomes 0. So, that means entropy remains constant. So, a reversible adiabatic process happens to be a isentropic process. Then moving further, there are some other philosophical thought of entropy process, since it quantifies the irreversibility, which means that higher is the increase in the entropy, there will be greater irreversibility. So, main parameters, for example, in a reversible adiabatic turbines, the maximum work is produced, whereas when you say irreversibility, turbine work gets reduced. So, in a reversible case, if a compressor consumes a least work when the processes are reversible adiabatic, but whereas when there is a irreversibility, the work input will be more. So, this is how the irreversibility parameter gets quantified through the term, that is entropy. Another significance point that I need to emphasize, that entropy is a measure of unavailable energy. That means, this energy cannot be possible for utilization, which means entropy is a disorderedness of the systems. Of course, we can, there is a law of entropy which says that entropy of universe continuously increases, and one point of time entropy will reach at its maximum. Now, when we say entropy is at maximum, which means all the matters will have same temperatures. So, when there is all the matters have same temperature, it is not possible for any extraction. So, that is a hypothetical situations. You will have all availability will be lost, all sources of energy will be lost, and that point human life will go to an halt. So, that is a philosophical thought process of entropy, but that is not a part of our discussions. Our main part is that entropy is a measure of irreversibility, and while you are looking at work extractions from a heat source. So, this is another example that we commonly come across, expansion of a gas, compression of a gas. So, when you say expansion of a gas, gas goes from high pressure to low pressures. So, the thermodynamic process that goes with respect to second law, fundamentally we call this an isentropic process, that is 1 to s, and when you say compression, it is the reverse case, that means process goes from 1 to 2 s. Here in the expansion process goes from 1 to 2 s in a reverse manner. Now, if the process is non-isentropic, we define the terms called as isentropic efficiency for work producing device and work consuming device. So, accordingly they are defined in terms of actual enthalpy change for an irreversible process. And if we say H is equal to Cp times T, so this was defined by first law, enthalpy is Cp times T for ideal gas, then enthalpy term reduces to temperatures. So, this is about the turbines and compressors, but when you talk about pumps, normally pumps do not have, because pumps have handles incompressible liquids and change in the temperature is quite insignificant. For that reasons, the pump process or pump work is defined by this V times delta P, and we introduce the pump efficiency eta P. So, this is also similar analogous terms when you define efficiency of a pump, because pumps handles incompressible liquids and change of temperature is insignificant for them. Now, another topic that we are going to touch upon is the pure substance. So, pure substance is a very vital analysis, because for all substances we are going to represent them in thermodynamic coordinates like pressure, volume, temperature, entropy, pressure, temperatures, different diagrams that can be drawn with thermodynamic viewpoints, and substances that are treated as mainly pure substance, which we can think that they are water, nitrogen, helium, carbon dioxide. So, all gases or whatever substance we say it is a pure substance, for them there are some characteristics, parameters or behavior that do exist. Either they are available in data form, or they are available in equation forms, or they are available in graphical forms. So, this is what we call as a properties of pure substance. Now, ideally speaking, when you say pure substance, there are three phase principle. One is solid, liquid and gas. So, and among them there is a change when the substance changes its phase state, we can go from solid to liquid phase, liquid to gas phase, of course, gas to solid, solid to gas, multiple number of ways substance can change its phase. Now, when there is a change in the phase, that means when we are going from liquid domain to gas domains, it passes through a phase change process, and during this phase change process whatever heat either that is consumed or it is liberated, extracted or comes out is known as latent heat. So, accordingly we define latent heat of freezings, latent heat of fusions, and of course, we can think of latent heat of vaporizations. So, these terms are associated with substance when it goes from the change of phase. Another point that we are going to have is that during a phase change processes, pressure and temperatures, temperatures are dependent properties. That means, either one of the parameter is sufficient to define the states, because during the phase change process the when there is a pressure change, that corresponding saturation temperature is also going to change. How we are going to look upon it? So, the first thing that we look at while deal with the property of pure substance, one is dryness fraction or quality, which was it is known that when you think a two phase systems, that means a liquid plus vapor in a containers. So, there are two parts, one is we can divide it in two parts, one is saturated vapor and saturated liquid, and they can be represented in pressure volume diagrams through this process. Now, when we have this pressure volume diagrams, we can see it said there is a dome, and within the dome we have liquid plus vapor, and one line that goes like from as there is a peak point which is called as critical point. So, left hand side of the critical point, that line we call this as a saturated liquid line, and right hand side of this will critical point we call this as a saturated vapor line. So, if you have a mixture of these two and at a given temperatures or pressures, we can fix its state as this saturated liquid or saturated vapor, and any other intermediate parameters, and each one will have its own specific volume, and any other parameter which is given within the dome, that is called a liquid vapor mixture. To define the states, we require a term called as quality or dryness fractions, and that is defined as x, which is nothing but ratio of mass of vapor to the mass of total mass. So, accordingly, and this equation can be framed, and once you know these dryness fractions, whatever properties are associated with that location at that state, we can find its average internal energy, enthalpy within this liquid vapor region. Then we have this saturation curve, that means, if you look at the change of state, that means, in the look at this figure temperature volume diagram, a substance, maybe it is let us say pure substance is water, it is at initial state 1, and that initial state which is at 20 degree centigrade, and if you keep add heat, so which means that temperature is continuously increasing to 0.2. So, when we are increasing temperature through this process, there is a temperature change. So, whatever temperature heat that gets added, we call this as a sensible heat. Then from 2 to 3 already it is at 100 degree centigrade. So, it is going to change its phase. So, 2 is the saturated liquid stage. So, when further heat is added, the 0.2 moves to 0.4, that is saturated vapor state, and further heat addition will go to state 5, which is called as a superheated regions. So, any other point which is 3, that is nothing but liquid plus vapor regions, and beyond 0.5 we will say superheated regions, and this curve is drawn at one particular pressures. So, similar way we can draw infinite number of curves, and locus of the curves goes in this manner, and we call this as a dome, and that dome consists of a peak point which is the critical point. That means, higher you go towards the critical point, we do not have two distinct points, saturated liquid and vapor. they try to merge together at a point that is called as a critical point. Now, this is also plot for pressure and volume. Other point is that when you take this for each pressure, there is a saturation temperatures. So, a curve that can be plotted corresponding to saturated pressure and saturated temperatures, and that goes in this manner. So, higher is the saturation temperature, higher will be the also saturation pressure. So, for water, the critical points are defined as 22 megapascal, 374.14 degree centigrade, 0.003155 meter cube per kg. Then moving further, we also are going to introduce the term which is called as a phase diagrams. So, phase means solid, liquid, gas, that are 3 different phase, but ideally speaking solid can change its state to liquid and liquid to vapor. So, this is the normal process that we go. So, solid, if you want to go to vapor, it has to melt, then after melting it will vaporize. So, it will go to vapor regions. Now, if the solid also can go to vapor directly through the process called as sublimation process. So, this particular diagram talks about pressure temperature, which is normally known as phase diagram. So, phase diagram, that means talks about a point, that means at certain pressure and temperatures, we can, it is possible to transfer from solid to vapor regions. So, for that region you have to go through the sublimation curve. Now, further, and if you go for higher temperatures, that means we will go out of, that means we will bypass this triple point and we will have to take the other routes, that is solid to liquid to vapor. So, that way through this process we define a point called as triple point, which means it is whatever thermodynamic processes are associated like melting, vaporization and sublimations, all the lines they merge to a point, and that is called as a triple point. So, in a phase diagrams, triple point is located by a unique point, and we have a critical point which is for a, that is defined at on this vaporization curve. Now, melting curve has two lines, one is given by the solid line, other is the dotted line. There are some substances that expand during freezing and some substance that contract during freezing. So, that way melting lines are defined in this manner. So, this is all about to talk about different points that we have during a phase change process. So, in this phase diagrams, we define the term that is triple point. One important point that I need to emphasize here, there are some numbers associated with this triple point for some substances like water, nitrogen, oxygen, carbon dioxide, acetylene, and on top of that, if you compare this atmospheric conditions, that is normally 101.325 kilopascal and 298 Kelvin. Now, comparing this, we will find that there are some substances that exist in this thing, and with respect to this atmospheric conditions, water has very low value of triple point parameters, whereas carbon dioxide have close to almost 5 times atmospheric pressures, and it has also temperature in the range of 216.55. So, that is way, that means it means that through this number it is possible to predict that for some substances it is possible we can go from solid to vapor line through this sublimation curve. One such example is the carbon dioxides. So, normally this is used for artificial rain and we call it them as a dry ice. Again, moving further, some other terms that we are going to use, that is compressed liquid, and this compressed liquid is also it's called subcooled liquid. So, that is defined not on the dome, rather if this is the dome, that is critical point in a temperature entropy diagram, temperature specific volume diagram, then we have a point, that is this is saturated liquid, saturated vapor, and before this saturated liquid whatever characteristics locations are there, they are called as compressed liquid region or subcooled liquid regions, and beyond this saturated vapor core we call this as a superheated regions. And to summarize everything, it is consolidated in two parameters, two diagrams. We have steam tables which is drawn for water, which we have already come across in our previous thermodynamics course. So, in a steam table we have, how do you view these steam tables? So, we have given all kinds of theoretical backgrounds. So, when you in a steam table there are called as saturated water temperature table, saturated water pressure table. That means, if you know temperature we can get back pressure, or if you know pressure we can get back temperatures. So, these two are interrelated property, and for each case all the parameters like specific volume, internal energy, enthalpy and entropy can be specified. Now, when you move on to superheated regions, we require two parameters to specify these thermodynamic states. One is pressure and other one is temperatures. So, two parameters, and on top of that we can have specific volume, enthalpy, then also we can have entropy. So, this can be specified. So, these are these extracts that are taken from the book Moran and Shapiro, just for visualization purpose. Another graphical representation of this water properties is done through a Mollier diagram. So, Mollier diagram is nothing but an enthalpy entropy diagrams, and it is very common, that justifies, and in fact, it is very vital to find the operating points for a steam power system. The next segment that we are going to introduce is the exergy and second law efficiency. So, exergy is the term that is used, that is derived from the second law, is that for any source of energy, if you want to quantify the work potential for that energy, then we call this as a exergy. So, energy is available in the kinetic form, it can be potential energy form, it can be a heat source, and corresponding work potential we can define. So, this particular expression says that if you have kinetic energy which is V square by 2, its corresponding exergy value or work potential we write as x k E, which is same as this, and for potential, because this kinetic energy is in the work form and potential energy is also in the work form, and so exergy is or work potential of the potential energy is also same. Now, for heat it is not possible. So, for that for to find the heat work potential, we have to introduce the Carnot cycle concept of heat engines. So, for x heat, that means work potential of heat source, that can be defined by 1 minus T 0 by T into Q. So, remember here T 0 stands for temperature of the environment or dead state. So, that means exergy is defined by keeping into consideration of environment into picture. So, if, and of course, if there is a mass flow, we can define this exergy of mass as m into psi. Psi is nothing but the specific exergy. So, in other words, in a flow systems, exergy can be defined by considering any arbitrary systems and surrounding into pictures. So, we can define them as this psi. So, based on this, we can, many books we can refer to find out what is the flow exergy and what is non-flow exergy and what is flow exergy. So, derivations are already there in the books, but however, I just need to emphasize the end expressions that we are going to use for our exergy calculations. So, for a closed systems, like we have a fixed mass systems, there is no mass interactions. So, entire system is defined through the exergy in terms of internal energy, of arbitrary state and this internal energy for the environment or dead state. So, correspondingly we can find the change in the exergy for a closed systems. In a similar logic we can find the flow exergy for an open system. One can be, so for that reasons we define this d phi and d psi. So, d phi stands for specific exergy terms associated with a closed systems, and that is defined through this internal energy change, then specific volume change, entropy change, kinetic energy change, potential energy change. Similarly, for flow exergy it is defined through enthalpy change, entropy change, kinetic energy change, potential energy change. So, only difference between these two is that here internal energy is replaced with enthalpy. Now, associated with this exergy we have this exergy principle which says that exergy of an isolated systems always decreases. So, entropy always increases whereas exergy always decreases, and in a limiting case in a reversible process it remains constant. And based on that, for an actual process we can say that exergy never increases, it always decreases, and when we have this when we say that exergy always decreases means it is destroyed. So, x destroyed can be specified as T 0 times entropy generations. So, this is similar to increase in the or law of entropy, it is also called as law of exergy. Law of entropy talks about increase in the entropy principle, law of exergy talks about loss in destruction of exergy. And to give a physical meaning of this, if this total energy available with us, and that is mainly with respect to work, heat, kinetic energy, potential energy, flow energy. So, all these things are available, but for each one there is a exergy, but out of this total energy the work potential, if you actually count, we will call this as exergy. Anything which does not have the work potential, we call this as a unavailable energy. So, this is nothing but whatever energy is going as a waste, and that is not possible to recover by any means. So, that is called as irreversibility. So, accountability of exergy will talk about irreversible nature of a process or cycle. Now, to quantify this term, what we define is called as a second law efficiency. So, we all know the first law efficiency which is derived by the Carnot from the Carnot cycles. Then we are going to have, but Carnot cycle, for that Carnot cycle we have this efficiency eta, and for the second law efficiency we are defining the same expression, but in a different way, is that is the ratio of actual efficiency to the maximum possible efficiency for same operating conditions. So, maximum possible efficiency is possible when the system is completely reversible, and we also take into account the system and its associated surrounding into pictures to find the what is the maximum possible reversible efficiency, and that is we take this ratio and we call this as a second law efficiency. And that term can be further found out that in terms of exergy, that is second law efficiency is defined by exergy recovered divided by exergy supplied, that is nothing but 1 minus exergy destroyed by exergy supplied. So, this is all about the overall concepts of thermodynamic viewpoint for the basic understandings. Now, with this knowledge will be the benchmark for our analysis in the subsequent modules. So, in the subsequent module we are going to discuss about steam cycle, gas turbine cycles and renewable systems. So, although this module is just a repetitions, but the concepts are very vital for our analysis in the subsequent modules. Now, whatever we discussed so far in these lectures, let me put out some numerical problems which will be helpful for understanding this thermodynamics concepts. So, the first problem talks about the entropy, and that is the benchmark for second point for the second law analysis. It tells that there is a heat source which is available at 537 degree centigrades, and it loses 1.5 kilojoule of heat to a sink. Sink means low temperature source, low temperature location, and there are two ways this sink is maintained. One case the sink is at 200 degree centigrades, other case sink is at 450 degree centigrades. Our job is to find out which is more irreversible. Now, to find the more irreversible, then we must find the what are the entropy change are associated in both the situations. Then only we can define this irreversible nature, and accordingly we will say that whether a particular that heat transfer process is more irreversible or not. So, thermodynamically we say there is a source which is available at 537 degree centigrades, and that is at, so I say that T h is equal to 537 degree centigrades, which is 810 Kelvin. So, in one case there are, in the first case it source rejects 1.5 kilojoule of heat to sink, and this sink is at 200 degree centigrades. And another case, same source with above temperatures, it rejects to sink at maintained at 450 degree centigrades. So, this is the, and here also it rejects 1.5 kilojoule of heat. So, case 2. So, here I can say T L1 as 200 degree centigrades means 473 Kelvin, and T L2 450 degree centigrade means 723 Kelvin. So, in both the cases our main intention is to find out what is entropy change for the case 1, that is minus Q by T H plus Q by, because heat is rejected from the source. So, entropy drops when heat is added to the sink, entropy is gained. So, that is minus 1500 by T H is 810 plus 1500 divided by T L is 473. So, delta S1, that is entropy change associated for the case 1, happens to be 1.32 kilojoule per Kelvin. And the second case, that is delta S2, is same expression we are using, that is minus 1500 by 810, but here the sink temperature is 723 degree Kelvins. So, it is 1500 by 723. So, this number happens to be 0.22 kilojoule per Kelvin. So, it is seen here that delta S1 is greater than delta S2, which implies heat transfer for process for case 1, maybe I can write case 1 is more irreversible. So, this is how we need to quantify the irreversible nature through entropy analysis. The second problem that we are going to discuss is about same irreversible nature, but through a analysis called as exergy analysis. So, in the second problem we have a closed systems, like you have a piston cylinder device. That piston cylinder device initially contains a gas, and in this case it is steam. So, it is a state 1, and that state 1 steam is 1 megapascal P1 and temperature is 300 degree centigrade. So, we say this is steam, and it expands to a final state. So, in this is the initial state. So, when it goes to final state, so that means this piston, when it expands to final state, we reach the state 2, and the state 2 is P2 is 0.2 megapascal, T2 is 150 degree centigrade. So, this is again in the superheated steam, and this data we need to find out from the steam table. So, this problem will also give how to refer steam table. Second thing, it gives the concept of exergy and second law. So, to solve the problem, first thing that we require is to get the property data using the steam table. So, for state 1, which is P1 1 megapascal, T1 300 degree centigrade, we can refer superheated steam table. So, superheated steam table will give you U1 is equal to 2793.2 kilojoule per kg, that is internal energy. Specific volume is 0.2579 meter cube per kg. Then entropy S1 is equal to 7.1229 kilojoule per kg Kelvin, and state 2 is defined as P1 0.2 megapascal, T1 as 150 degree centigrade, and again we have to use superheated steam table. So, so P2, so it is P2 T2, and we have U2 is equal to 2576.9 kilojoule per kg. V1 is equal to V2 will be equal to 0.9596 meter cube per kg, and S2 is 7.2795 kilojoule per kg Kelvin. Additionally, we have to take the dead state. So, dead state is outside atmosphere, outside this piston cylinder device. So, this dead state is defined by pressure P naught T naught, and this dead state case, at these conditions we have to find the water properties, or that is at P is equal to, or P naught 100 kilopascal and T naught is equal to 300 Kelvin. Then we have U0 104.88 kilojoule per kg, S0 is equal to 0.3674 kilojoule per kg Kelvin, V0 is equal to 0.001 meter cube per kg. So, the first problem that we are going to find, what is exergy. Exergy is defined as exergy at initial state, that is, since it is a closed systems, we write m times u minus u0 plus u minus u0 minus T0 into S minus S0 plus V0 into V minus V0. So, this is the general expressions. So, I change this to x1. So, x1 means we have to replace u as u1, S as S1, V as V1, and here we also have the mass of this steam, that is 0.04 kg. So, we write this 0.04 and put this state 1 points 2793.2 minus 104.88 minus T0 is 300 into 7.1229 minus S0 0.3764 plus P0 101 100 kilopascal, V minus V0, V1 is 0.2579 minus 0.001. So, entire bracket if you calculate, we will say x1 is equal to 27.5 kilojoule. Similarly, for state 2, x2 can be calculated as 19.8 kilojoule. So, that means replace u, s and v by state 2. So, that means then we can answer the second part, exergy change, that is delta x is equal to x1 minus x2, that is 7.7 kilojoule. Then third part, exergy destroyed. So, exergy destroyed is equal to delta x minus W u. Now, to calculate W u, we have to use this equation W u, that is for a closed system, that is q minus delta u, delta u. So, W u because is equal to q, q is minus 1.5 because heat is rejected, and delta u is u2 minus u1, that is m times small delta u, and so this means W u is equal to minus 1.5 because heat is rejected minus m times is 0.04, delta u is u2 minus u1, that is 2576.9 minus 2793.2. So, W u becomes, so 2 negative quantity, so the W u becomes 7.15 kilojoule. So, W u known, so we can say x destroyed is equal to 7.7 minus 7.15. So, that is 0.55 kilojoule, and last one is second law efficiency. So, second law efficiency we write by basic definition W u by x1 minus x2. So, this number becomes 7.15 by 7.7. So, second law efficiency is equal to 0.928. So, approximately 92.8%. So, it means that this particular problem gives an indications there is a in this stream there is a quite a significant amount of work potential which is not possible to extract. That means, still we have ability to get maximum work out of this, but however, the system does not allow to get it extracted. So, that means, you will have very high destruction in this particular closed systems. So, this is the indication that how you are going to calculate exergy and how it is linked to the irreversible nature of a thermodynamic process. So, with this I conclude. Thank you for your attentions and best of luck.